Auto-negotiation. The Ethernet auto-negotiation mechanism is a physical layer protocol that allows two connected devices to automatically determine and configure the optimal link parameters for communication. This process, defined primarily in Clause 28 of the IEEE 802.3 standard, originally known as N-way, ensures the highest possible performance and compatibility between devices with differing capabilities. How auto-negotiation works. The process involves a few key stages. 1. Capability exchange, fast link pulses, FLPs. When two auto-negotiation capable devices are connected, they exchange information about their supported operating modes using a series of specialized signals called fast link pulses, FLPs. FLPs are based on the normal link pulses, NLPs, used in older 10BASE-T Ethernet for link integrity testing but are sent in bursts. Each FLP burst contains a 16-bit link code word, LCW, where the bits indicate support for different speeds, 10 Mbps, 100 Mbps, 1000 Mbps, etc., duplex modes, half or full, and flow control. 2. Priority-based resolution. After receiving the capabilities from the peer device, both devices compare the information. They select the highest performance common operating mode they both support. The standard follows a priority order, generally favoring higher speed over lower speed. Full duplex mode over half duplex at the same speed. 3. Mode configuration. Once an agreement is reached, both devices configure their physical layer interfaces to the negotiated settings, example 1000 Mbps, full duplex, and begin normal data transmission. 4. Master-slave resolution. For gigabit Ethernet and higher for 1000 BASE-T, gigabit Ethernet, and beyond. Auto-negotiation also determines which device acts as the master clock source and which acts as the slave to ensure proper timing synchronization. Parameters determined. The auto-negotiation process determines several crucial link parameters: speed, the maximum data transfer rate, example 10/100/1000 Mbps. Duplex mode, whether communication can happen in only one direction at a time, half duplex, or both directions simultaneously, full duplex. Flow control, the ability to use pause frames to temporarily stop data transmission to prevent buffer overflow, IEEE 802.3x. When one side of an Ethernet link supports auto-negotiation, but the other side does not, or has it disabled, the connection typically falls back to a default operational state based on the auto-negotiating device's behavior. This scenario often leads to a link connection but frequently results in a suboptimal configuration known as a duplex mismatch, which causes severe network performance issues. Here is what generally happens. The behavior of the auto-negotiating side. The device that has auto-negotiation enabled sends fast link pulses, FLPs, to attempt the negotiation process. If it receives FLPs back from the other side, negotiation proceeds normally. If it receives only normal link pulses, NLPs, the simple pulses used by legacy 10BASE-T devices, or no negotiation pulses at all, the auto-negotiating device initiates a fallback mechanism called parallel detection. Parallel detection rules. Through parallel detection, the auto-negotiating device determines the speed of the link by analyzing the type of electrical signals it sees from the non-negotiating device. The auto-negotiating device makes the following assumptions: non-negotiation side's auto-negotiating side duplex mode assumed speed assumes 10 Mbps, 10 BASE-T, 10 Mbps half duplex 100 Mbps, 100 base 100 Mbps half duplex TX, 1000 Mbps, 1000 base full duplex. This specific speed forces full 1000 Mbps T, duplex. The problem: duplex mismatch. The major issue arises at 10 Mbps and 100 Mbps speeds. The auto-negotiating side correctly detects the speed but defaults to half duplex mode because negotiation failed. The non-negotiating side is often manually configured for full duplex, a common configuration choice for maximizing performance when auto-negotiation is off. This mismatch creates a situation where the half duplex side expects to manage all traffic collisions and will wait after transmitting. The full duplex side assumes it has dedicated transmit and receive paths and will transmit whenever it has data ready, potentially ignoring the half duplex side's transmissions. Result: a massive number of late collisions, frame discards, and constant retransmissions occur, causing network throughput to drop drastically, often to only 10% of the nominal speed. Solution: to prevent these issues, the best practice is to ensure a consistent configuration on both ends of a link. 1. Enable auto-negotiation on both sides, the recommended approach for all modern equipment. 2. If manual configuration is unavoidable, manually force the exact same speed and duplex mode on both sides of the link. In modern and multi-gigabit Ethernet standards, auto-negotiation is mandatory for copper twisted pair links. It is no longer an optional feature as it was in the earliest Ethernet versions. For all speeds of 1 Gbps and above over copper cabling, auto-negotiation is required by the IEEE 802.3 standards to establish a working link. Auto-negotiation in newer standards such as 1000 BASE-T, 2.5 5 and 10 all mandate the use of auto-negotiation for several technical reasons beyond just speed and duplex matching. 1000 Gigabit Ethernet auto-negotiation is mandatory to determine the master/slave roles for clock synchronization between the two connected devices. Without this timing setup, the link will not establish. 2.5 and 5 N/IEEE 802.3BZ. These intermediate speeds, designed to work over existing Cat5e/Cat6 cabling, also require mandatory auto-negotiation. They use extensions to the standard negotiation protocol, extended next pages, to advertise and agree upon these specific multi-gigabit speeds, as well as handle the master/slave clocking roles. 10 Gigabit Ethernet auto-negotiation is mandatory for 10 implementations to manage link training, advertise capabilities, and set up parameters like energy-efficient Ethernet, EE. Why is it mandatory? In high-speed Ethernet, achieving reliable communication requires more complex configuration than just speed and duplex. Auto-negotiation handles critical physical layer functions automatically. Master/slave timing. High-speed copper Ethernet requires one device to be the primary clock source, master, and the other to synchronize to it, slave. This is negotiated automatically. Link training. At 1G and faster speeds, the physical layer transceivers perform complex link training procedures involving adaptive equalization and echo cancellation to optimize the signal over the specific cable being used. This training is part of the auto-negotiation process. Flow control and EE. Auto-negotiation also sets parameters for optional features like flow control, pause frames, and energy-efficient Ethernet, EE. Best practice today: manual configuration, forcing speed and duplex, is strongly discouraged for modern Ethernet, 1G and above, because it disables these crucial link establishment functions, often resulting in no link or an unstable link, rather than just a duplex mismatch. Network equipment manufacturers universally recommend using auto-negotiation on all access ports. Benefits and best practices: ease of use, automates link setup, reducing the need for manual configuration and potential human error. Interoperability, ensures compatibility between devices from different manufacturers and generations. Performance optimization, guarantees that the link operates at the highest possible shared speed and duplex mode. For reliable operation, manufacturers generally recommend enabling auto-negotiation on all access ports by default. Duplex mismatches, a common problem with manual configuration, example one side forced to full duplex and the other set to auto-negotiate, resulting in half-duplex assumption, are largely eliminated when both sides use auto-negotiation. Ethernet auto-negotiation offers significant advantages in network management but can introduce specific challenges, particularly when dealing with legacy equipment or misconfigurations. Advantages of auto-negotiation: auto-negotiation is the recommended and default configuration for most network devices today due to several key benefits: simplified deployment and management. It eliminates the need for manual configuration of speed and duplex settings on every network port, saving time and reducing human error during installation or device replacement. Optimal performance: devices automatically select the highest possible common speed and prefer full duplex operation, maximizing bandwidth utilization and network efficiency. Ensured compatibility: the mechanism allows devices from different vendors and generations, example 10 Mbps, 100 Mbps, 1 Gbps devices, to connect and operate seamlessly by finding a mutually supported mode. Automatic upgrades: when you replace an older device with a newer, faster one, the link automatically adjusts to the new, higher speed without manual intervention. Required for advanced features: for modern speeds, 1 Gbps and higher, auto-negotiation is mandatory. It negotiates essential parameters like master/slave clock synchronization and flow control, pause frames, which are vital for link stability and performance. Common issues of auto-negotiation: while modern implementations are highly reliable, issues can arise, often stemming from interactions with older or misconfigured equipment. Duplex mismatch: this is the most common and severe problem. It occurs when one device is set to auto-negotiate and the other is manually forced to a specific full duplex speed. The auto-negotiating side defaults to half duplex, via parallel detection, leading to severe packet loss, high collision rates, and dramatically reduced throughput. Link performance may drop to 10% of nominal speed. Link failure or instability: if the negotiation process fails to reach an agreement, example neither device supports a common mode, or the link is unstable due to bad cabling, the link may not activate at all. Inconsistent vendor implementations: early Ethernet standards had some ambiguity, leading to slight variations in how different manufacturers implemented auto-negotiation. While less common today, varying behaviors between devices can cause connectivity issues. Troubleshooting complexity: when a link problem occurs, especially intermittent performance issues caused by a duplex mismatch, diagnosing the root cause can be difficult and time-consuming, requiring the use of network analysis tools or manual configuration checks. The auto-negotiation mechanism in Ethernet is a physical layer protocol designed for the automatic setup of the most optimal link configuration between two connected devices. Here are the key features of auto-negotiation. Feature description: automatic speed automatically identifies and selects the highest shared data rate supported detection by both devices, example 10 Mbps, 100 Mbps, 1 Gbps, 10 Gbps. Duplex mode selection negotiates whether the link will operate in half duplex, one-way traffic at a time, or full duplex, simultaneous two-way traffic, mode, favoring full duplex where possible. Uses fast link pulses, FLPs, to broadcast the device's supported modes to capability exchange its link partner. Follows predefined rules, standardized by IEEE 802.3, to select the best priority resolution possible configuration, prioritizing higher speeds and full duplex modes. Parallel detection: a fallback mechanism that allows an auto-negotiating device to detect the speed of a non-negotiating device, example legacy equipment, and establish a basic link connection. For gigabit Ethernet and faster standards, it is essential for negotiating master/slave timing which device controls the link clock, master, and which synchronizes to it, mandatory for 1G+, slave. Support for advanced negotiates optional features like IEEE 802.3x flow control and energy features. Efficient Ethernet, EE. Mandatory for modern, required for all speeds 1 Gbps and above over copper twisted pair cabling Ethernet for the link to function correctly. In summary, the primary feature of auto-negotiation is its ability to establish reliable, high-performance links with minimal human intervention, ensuring interoperability across a wide range of Ethernet hardware.